This is a video for Geometry Chapter 7, Section 4, in which we are looking at triangles that have a couple things cutting those triangles into proportional pieces, one being an angle bisector, the other is parallels to sides of triangles, which is what this video is going to talk about. We're going to talk about parallels in triangles as well as parallels with transversals. So I have a triangle and we have parallels to one of the sides of the triangle, or we could have these these blue transversals with parallels, and we're going to talk about the proportionality, the proportional pieces that are created by these parallel lines. First, looking at a triangle here, and it's got parallel side. It has a segment that is parallel to one of the sides, and it's cut that large triangle so that the left-hand side now has two pieces to it, piece A and piece C, and the right-hand side has two pieces, piece B and piece D. And with the parallels, we have a pair of corresponding angles and a second pair of corresponding angles. So the parallel segments created corresponding congruent angles. And when you have two pair of congruent angles in two different triangles, you end up with similar triangles. Well, if we have similar triangles, we have proportional sides. We have a small triangle that has a side A and B, but we need to talk about the sides of the large triangle. So we notice that the large triangle, the left-hand side is A plus C, and the right-hand side is B plus D. So we now can compare these proportional sides of the small triangle to the large triangle. So A is to A plus C as B is to B plus D. We can cross multiply, and then we'll distribute to simplify. AB plus AD equals AB plus BC. Subtract the AB that's on both sides, and we end up with AD equals BC. I'm going to now divide both sides by B times D, and we're going to have some cancellation, some simplification that will happen, and we're left with A is to B as C is to D. Well, that means I'm comparing the small piece A on the left to the small piece B on the right, and that ratio is going to be exactly the same as the other piece on the left, C, is to the piece D on the right. Let's look at this again in the triangle. So we've got the triangle here, same situation, and we just talked about that the pieces A is to B is equal to C is to D. We will get the same reduced ratio regardless of what the numbers are to begin with. They're going to always reduce to the same fraction. And remember, in this particular case, I am chosen to compare the left side to the right side. We could have compared the right side to the left side instead, but this is where I'm going. So from now on, I'm always going to keep that same left side to the right side while I'm doing this demonstration. Now, I'm going to extend this triangle, make it a little bit larger, by extending it and then having another parallel piece. And what's interesting here is I could go through the same process that we just went through to prove the other four pieces have a proportionality statement. The main thing is F to G will give the same ratio as well. And what's really interesting about that is I can move this parallel line anywhere I want, and that's still going to be true. If I make C and D much shorter, this proportionality statement is still exactly the same. I could make F and G, if I brought it way down, that tiny little F and G, that proportionality statement would still be the same. And it's not just this segment that I can move. I can move the other parallel segment that went up by A and B. I could make this one real tiny. It could be a tiny, tiny triangle up there, or make this one really close to C and D. I'm still going to get a proportionality of the pieces. Not only that, but I could just draw another parallel line and make another pair of pieces, M and N, and as long as I'm comparing the same direction, on this particular case, I'm comparing left to right, M divided by N will give me the exact same ratio as well. So this is when you have a parallel segment or line cutting through a triangle, that it creates these proportional pieces. Now let's look at transversals. Well, in this case, I have these two blue transversals. I have 5 parallel lines, which cuts it into 4 pieces on the left and 4 pieces on the right. And just like it did with triangles, those pieces will be proportional. If you think about it, these two blue lines will eventually meet because they are not parallel, and then it would look like a big triangle, and so it becomes the same idea as the previous case. If the transversals were parallel, then each one of these little areas, these little sections in here, this little piece right here, this would become a parallelogram. And then opposite sides would be equal, which would be a 1-to-1 ratio, and so all of them would be parallelograms. So it works whether or not these transversals are parallel or not parallel. The fact remains that the pieces that the parallels cut the transversal into, these pieces, A and B and C and D and M and F and G, they're all proportional.